Hello everyone, I'm Dr. George Bartuska with the Florida Aviation Network. Welcome to Sky Insights. Today we're going to be talking about visibility and flight into IMC conditions. IMC stands for Instrument Meteorological Conditions. The physics of meteorology and visibility is a complex subject. We would normally be doing this in a one-day seminar, but I've only got about 30 minutes, so I'm going to hit the high points from a meteorological point of view. We're going to be talking about VFR, Visual Flight Rules. Some of you watching this are brand new to aviation, so we're going to cover the basics first and then get into fog. Why do we care about visibility? Well, to prevent accidents and save lives would be a very good reason. But I'm using as a guide a research study that was done by Northern Illinois University in 2016. And here were the main results of that research. Total GA operations right now result in about 765 fatalities every year. Weather is a contributing factor in 25% of those accidents, or a quarter of all accidents. For more than 100 years of aviation, fog and sleet, that we now call icing, has been identified as a weather hazard. Student pilots can miss 100% of the weather questions and still pass their FAA exam. That was in 2016. That part is changing. The maximum weather hazards right now identified in accident analysis are wind, low visibility, low ceilings, and high density altitude. At least 50% of restricted low visibility accidents are fatal. Research efforts also research suggests we should focus on pilot weather instruction, education. That's what we're doing today. Despite efforts, there's still about 100 deaths, weather-related deaths every year. Although wind is the most common weather hazard, only about 8% of wind accidents are fatal. Fog, however, is associated with 40% of all fatal accidents. VFR pilots scud running with get-home-itis fatally fly into IMC conditions. In other words, they encounter clouds, and instead of turning around, they try to make it back and don't make it. Now, where are the most fog-prone areas in the United States? Those are California, the Pacific Northwest, the Gulf Coast, the Appalachians, the Great Lakes, and New England. Here's one representation of that. We can see the Northeast, the Northwest, the California coast, the Gulf Coast, around the Appalachian Mountains, and around the Great Lakes. Here's another representation from NOAA that kind of shows the same thing. That doesn't mean we don't have fog anywhere else. We can have fog just about anywhere, but this is where it's most common. Now, if you're new to aviation, let's define VFR. VFR is a set of regulations and procedures governing aircraft operations when visibility and weather conditions allow for visual navigation and reference to the ground. VFR allows pilots to operate aircraft by visually navigating with reference to the ground, landmarks, and airspace visual markers. It is key to acknowledge that this requires clear visibility. You have to be able to see the ground, and is typically accomplished during good weather conditions. Title 91 of 103 requires that all pilots, quote, before beginning a flight, become familiar with all available information concerning that flight, end of quote. Part 91.3 stipulates that pilots in command of an aircraft are directly responsible for and the final authority as to the operation of that aircraft, end of quote. Thus, pilots are solely responsible for knowing everything there is to know about the weather along their planned route of flight. Now let's do some definitions of the different kinds of visibility. Flight visibility. This is the visibility you have when you're in the cockpit looking out the window. The average forward horizontal distance from the cockpit of an aircraft in flight at which prominent unlit objects may be seen and identified by day, and prominent lighted objects may be seen and identified by night. Ground visibility, or RVR, runway visual range, is typically what you see in the METAR. Horizontal visibility near the ground is reported by the National Weather Service or other accredited observers. For takeoffs and landings, the ground visibility must be at least 1 statute mile. And like I said, this is what you'll see in the METARs and the TAFs. Slant visibility is the distance the pilot can see from the cockpit down to the ground. Is more relevant when we're on final approach in compromised visibility conditions, or we're trying to navigate looking at landmarks on the ground. However, it's not mentioned in the FARs. Now here's a graphic representation of what we just talked about. Horizontal visibility or flight visibility is looking straight ahead when we're flying. Ground visibility is what you're given as relates to the runway, the RVR, and slant visibility is either during navigation or when we're getting ready to land. Now, airspace visibility requirements. All pilots have to learn the different visibility requirements per airspace. And this is the chart they have to memorize, that we have to memorize, and tells you how many statute miles you have to have a visibility and what the distance is you have to keep away from the clouds. And you'll be tested on that with tests like this. What is the minimum flight visibility and proximity to cloud requirements for VFR at 6,500 feet, mean sea level in class C, D, and E air for airspace? The answer is, first one, 3 miles visibility, 1,000 feet above and 500 feet below. That's what all pilots have to know. But what we're talking about today is what is going to cause a visibility problem. Here are the main things that can appear as obstruction in the METARs. Haze, dust. Right now we have lots of dust blowing off the deserts in northern Africa, moving towards the east coast of the United States. Forest fires. We've been having fires in Canada, in California, in Pennsylvania, in New York, so smoke can be a real big problem. Right now, the Mount Kilauea in Hawaii has been erupting, so there's ash problems in the Hawaiian Islands. Spray near the ocean or lakes, sand where there's deserts, fog and stratus, which is what I'm going to talk about, and of course then there's heavy rain, heavy snow, and blowing snow. Now, our most lethal weather hazard is fog. Pilots call it soup or pea soup. Everybody is affected by fog, whether you're driving a car, whether you're in a ship at sea, whether you're in a rail situation. This is a picture after an accident took place during fog, or whether you're in an aircraft. Now let's define fog. Fog is defined as obscurity in the surface layers of the atmosphere, which is caused by a suspension of water droplets or ice crystals. Haze is a suspension of extremely small dry particles in the air, not water droplets or ice. Particles that are invisible to the naked eye, but sufficient enough to give the air a milky appearance or rainbow-like array of colors, similar to an oil slick. Mist is another form of fog, but very light fog. Mist is still the result of suspension of water droplets and ice crystals, but simply at a lower density. Mist forms a thin gray veil over the landscape. Now, one of the things we're going to talk about today, because it affects us all in driving, is a pileup that occurred on Interstate 4 here in Central Florida on January 9th of 2008. We've had these kind of pileups all over the United States and all over the world, but this one there's a lot of data on. In this one, there were 70 vehicles involved, 4 people killed, 38 people injured, and 5 seriously. I'm going to talk more about that later because we have good information. We're concerned as pilots with radiation fog, advection fog, and upslope fog. Those are the main things we're tested on, but we're also concerned with freezing fog, evaporation fog, and hail fog. Now, fog can be a complex and complicated weather phenomena, thus we will repeat some things and jump around to keep it interesting. Let's take a look. Fog is a visible aggregate of minute water droplets forming on the Earth's surface or on the ground. By definition, fog reduces horizontal visibility to less than 5/8 statute miles or 1,100 yards or 1 kilometer, Unlike drizzle, fog does not fall to the ground. It stays right on the ground. Fog is a cloud. However, its base must be at the Earth's surface. Fog forms when the ambient air temperature, or the outside air temperature, and the dew point temperature of the air are identical or nearly so. This may occur through cooling of the air to its dew point, or by adding mixture and thereby elevating the dew point. Fog seldom forms when the temperature-dew point spread is greater than 2 to 3 degrees centigrade or 4 to 5 degrees Fahrenheit. Now the question is, what is the dew point? What is dew? Well, we've all had a glass of soda or a bottle and seen this water on the outside. And when I used to teach earth-based science and ask students, what is that water? Some kids would say, well, maybe there's a leak in the bottle. Nope. So let's talk about that. When we talk about humidity, we're used to talking about relative humidity. The common man knows exactly what we mean by relative humidity, but the dew point is a little more vague. But the dew point is the actual measure of moisture in the air. So when the dew point temperature equals the ambient temperature, the relative humidity is 100%. And we say the atmosphere is saturated. We have atmospheric saturation. This causes condensation and cloud formation. Fog is just a cloud on the ground. Just a couple real quick things here. Heat transfer. Sensible heat is when the heat moves from a colder area to a warmer area. Latent heat transfer is when we have a phase change, such as in evaporative cooling or condensation like we saw on that bottle a minute ago. Evaporative cooling, like when you get out of the swimming pool, no matter what the temperature of the water or the air is, you're going to feel cold because the water is sucking the heat out of your body to change from a liquid to a gas. That's condensation, and heat is given off. Now, if fog's just a cloud on the ground, how do we get a cloud in the first place? Well, the sun is the source for all the energy of weather on Earth, but to get a cloud, we must have water. We must have water vapor in the atmosphere. We usually relate this by talking about a partial in meteorology, or a blob of air, which acts just like a hot air balloon. If we take this example, this is South Daytona Beach here in Florida, near Daytona Beach. Let's pretend that car on the left with the luggage rack is our car. We get to the beach, we leave our towels in the car, we go out in the beach to go swimming, and we're out there for about an hour. We come back to the car, it's in the middle of the summer. We open the car door and it's now about 150 to 180 degrees Fahrenheit. And when we open that door, a blob of hot air comes out. And it's just like a hot air balloon. It starts to rise. As it rises, it expands. As it expands, it cools. And you can see there's no clouds in the sky right now, so it'll probably go up to around 500 feet. And at that point, it will have cooled to the same temperature as the surrounding air. And that's it. It stops and it will start to fall back down. Now, let's say we take those towels out of the car and dry off, and if you're at Daytona Beach in the summer, you can look any direction and there's a hot dog stand. So we're going to take all our wet towels, let's say there's 4 of us, and throw them in the car, back in the car, lock up the car and go down to the hot dog stand. And while we're there, we're going to run into some friends and we're going to talk for about an hour. Now we're going to come back to that car and open the door, and once again, a very hot 150 to 180 degree temperature blob is going to come out of that car, and it's going to start to rise again, but a little slower because it's now fully saturated from all the water that was in those towels. And it will again rise and it will start to expand, and because of expansion it will cool. But this time, hypothetically at 5,000 feet, it will have cooled to the dew point and it will form a cloud. And when it does, it will give off the heat and it will start going even faster if there's no inversion to make it go up. And this is what we call thermals if you're a glider pilot. If you're talking about thunderstorms, this is what's causing the updraft in a thunderstorm. Now, if we were talking about major weather storms, that initial point where the dew point forms is called the lifted condensation level. If it can get positive buoyancy and keep going, it reaches the level of free convection, and it will go until it condenses out all its water. But in the case of fog, we just get to the lifted condensation level, and that's the fog on the ground. Now, fog's just a cloud on the ground. These, once again, are the types of fog that we're concerned with. Let's talk about radiation fog. Radiation fog is produced over land area when radiational cooling reduces the air temperature to or below its dew point. Thus, radiation fog is generally a nighttime occurrence and often does not dissipate until after sunrise. So as it gets dark, the land starts to cool through radiation, through electromagnetic radiation, and once the heat is gone from the ground, the air, if it has moisture in it in contact with the ground, through conduction, will cool down and fog will form because it will cool the air to the dew point. Just a couple quick terms of heat flow. Radiational cooling or radiational heat transfer is the same way the sun heats us all the way through space. Conduction means we're actually in contact with something, and convection means there's a fluid involved. Once again, radiational fog is on the surface. Advection fog, the other main kind of fog we have, advection is a fancy name for wind. means horizontal movement. Advection fog forms when moist air moves over a cooler surface, and the subsequent cooling of that air is below the dew point. This is what happens in San Francisco. Most common along coastal areas, but often moves into the continental areas, and it's also called sea fog. Here we have that typical situation on the west coast of the United States. Big difference between the west coast and the east coast of the United States. The west coast has no continental shelf, so the water goes down 3,000 to 4,000 feet right off the coast. Thus we get an upwelling of cool air, and if we have a warm moist air mass start moving towards the coast, it's going to get cooled down by that water, it's going to condense, and we're going to get fog. The same thing can happen in the winter when we get warm air coming up from the Gulf of Mexico over colder land, or especially over snowland. It's going to cool down that air and we're going to get fog. Now let's talk again real quick about this accident. Here is the actual weather map on the day of January 9th, 2008. And just so you know, any date you want to know for the weather maps, all you have to do is Google daily weather maps, and on the left you can select the year, the month, and the day. And just to review, if you're not familiar with, recent reading surface weather maps, the towns all have a surface model, and in that surface model the temperature is in the upper left hand corner, the dew point is in the lower left hand corner. So here the temperature is 57 degrees, the dew point is 56 degrees. And remember what I said, if they are within a couple degrees of each other, the dew point and the temperature, we're going to get fog. In this picture in the center of the state of Florida, you see the number 214. That was the barometric pressure in Tampa at the time. But right under the number 1 of that 214 is where that accident took place. Well, look, here is the temperature and dew point of Orlando. 53 temperature, 53 dew point. They're the same. The air was fully saturated. There definitely was fog. Look at Jacksonville. 56 was the temperature, 56 was the dew point. Definitely fogged in. And Tallahassee, Florida, 57 temperature, 57 dew point. All the atmosphere in northern and central Florida was in a fog state. Now, how do we measure fog? When the temperature and dew point spread is less than 5 degrees, 4 or 5 degrees Fahrenheit, or 3 or 4 degrees Celsius, we can expect fog. Unlike relative humidity, dew point is a measure of the actual water vapor in the air. This is the temperature to which must be cooled in order to become saturated and therefore reach 100% relative humidity. At this point, fog or clouds must form. And the way we measure it is with a sling psychrometer, which has 2 thermometers, and one has a wick. You can't see it in that picture, but if you look here, you can see right here that this thermometer, called the wet ball thermometer, has a wick on it, and we get that wick wet, and when we sling it around like the observer lady is doing in the right-hand side, she's at Mount Washington in New Hampshire, we're able to take a reading and calculate the dew point. Okay, one other kind of fog that we encounter is upslope fog. As the partial of air ascends up the slope of a mountain or a hill, it expands and cools just like it did on the beach, and it cools down to the dew point and a fog or cloud will form. We need wind to move it up the slope, and we need a slope. Now, real quick on frontal, here's a quick diagram of a cold front on the top. You can see the cold, dense air acts like a wedge to move under the warm air. On the bottom with a warm front, the warm air stretches out over the cold air and sinks down into it. In the case of a warm front, fog will form just past the beginning of the frontal boundary because you have the warm air mixing with the cold air. In the case of a cold front, the fog can form just past the leading edge of the front because once again we have the cold air mixing with the warm air. Here's a really cool diagram out of a book that shows radiation fog in the upper right-hand corner, advection fog in the lower right-hand corner, upslope fog on the top, and frontal fog on the left. Now, we're going to be flying, somebody's going to be flying their airplane, and if they haven't done a really good job of planning for weather, they're going to encounter clouds or fog. We call this inadvertent VFR flight into IMC, Instrument Meteorological Conditions. They're called instrument meteorological conditions because by law you can't fly into a cloud without instrument rating and an instrument flight plan. In most cases, an inadvertent entry into IMC will be best resolved by a 180-degree turn to fly back into the VFR conditions you came from. This maneuver needs to be planned before attempting to execute the turn. You need to make sure you're aware where you're at when you're going to turn, so you don't turn into the side of a mountain or turn into a high transmission tower. Visual flight rules, or VFR flights that inadvertently or intentionally, why would you fly intentionally? Because you're trying to get home, enter into instrument meteorological conditions, continue to be a significant safety hazard to GA pilots. Although loss of control and controlled flight into terrain accidents by VFR pilots in IMC typically account for a portion of the total GA accidents, such occurrences count for 75% of all the weather-related fatalities. It's the 75% of what kills our pilots and their passengers on board. So why don't pilots just turn around? Get home-itis, gotta meet a deadline, can't be late, press on itis, can't let the people down. Well, unfortunately, the people you're trying not to let down might be your spouse and your family in the back of your plane. This is the time you've got to turn around, or you could possibly end up dead with everybody on board. So, the saying is, land and live. Turn around, find a place to land, check the weather, and wait for another time to go. And that's whether you're a private pilot or a corporate pilot. The airlines don't have to worry about this because they're flying on instruments. So I hope you enjoyed my presentation today. Thank you for joining us. This is Dr. George Bartuska with the Florida Aviation Network. I'll see you next time with another weather topic.